Welcome to Nighttoria. It's lovely to have you here tonight. Wherever you are right now, whatever corner of the world has gone quiet around you, I'm glad you found your way to this little patch of calm. Maybe you're under a blanket with the lamp still on. Maybe you're on a couch with the day finally behind you, or on a long train, or somewhere far from home where the night feels a little strange. Wherever you are, settle in, get comfortable. There's nothing you need to do for the next while except breathe slowly and let the world get a little softer. And before we drift off into the sky together, if you enjoy these slow journeys and you'd like more nights like this one, a gentle like and subscribe really does help this sleepy little channel keep going. Small creators like me lean on that quiet support more than you'd think. And to everyone who's already here, already part of this, thank you. Truly. You make these nights possible. So while you're getting comfortable, tell me, if you feel like it, where in the world are you watching from tonight? What time has it gotten to in your corner of the dark? I always love to imagine all the different places the night is touching while we talk. Now I'll make you my usual gentle promise. I'm going to try not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something lovely about the sky on your way to sleep. A fair trade, I think. And here's the more important promise. We're going to take this slowly, softly, one idea at a time, with plenty of room to breathe between them. You don't have to follow every detail. You don't have to hold on to anything. If you drift off halfway through, that's perfectly fine. The ideas will still be here, patient and waiting, the next time you come back. There's no rush tonight, none at all. So let me tell you what we're going to wander through gently while you fall asleep. There is something enormous burned into the sky above and below our galaxy. Two of them, actually. Two vast bubbles, each one stretching about 25,000 light-years tall. That's roughly a quarter of the way across the entire Milky Way, rising up out of the center of our galaxy like the two halves of a colossal hourglass. One bubble reaches up, one reaches down, joined at the middle where our galaxy's heart is. And here is the strange, quiet thing I want to share with you over the next while. At the center of all of this, at the point these two enormous bubbles seem to be growing out of, sits a black hole that is, right now, tonight, almost completely silent, almost completely still, practically asleep. And yet something tore those bubbles into the sky. Something at that quiet center, long ago, woke up and roared. But I'm getting ahead of myself. Let's slow down. Let's go back to the beginning of this and take it one soft step at a time. For a very long time, nobody knew the bubbles were there at all. They're not the kind of thing you can see by simply looking up. If you went outside tonight, found a dark field far from any city lights, lay back on the cool grass and stared up at the band of the Milky Way arching overhead, you would see none of this. Your eyes simply aren't built for it. The bubbles glow in kinds of light our eyes can't catch. Gamma rays, the most energetic light there is. Light far beyond the violet end of the rainbow, far beyond anything our soft human eyes evolved to notice. It's a little like how a dog can hear a whistle that's completely silent to you. The sound is there, filling the room, perfectly real. Your ears just aren't made to receive it. The sky has always been singing in these high, invisible notes. We simply couldn't hear them. Not until we built ears that could, and we did build them. In the year 2010, a team of astronomers, among them a researcher named Doug Finkbeiner, were poring over data from a remarkable instrument called the Fermi Gamma-ray Space Telescope. Picture a telescope, but not the kind you might have at home, with a tube and a lens you press your eye against. This one orbits high above the Earth, above all our atmosphere, because our atmosphere, bless it, it keeps us alive, also blocks most of these high-energy rays from ever reaching the ground, which is a good thing for us, frankly. But it means that to see the sky in gamma rays, you have to lift your eyes up above the air itself. So Fermi floats up there in orbit, slowly sweeping its gaze across the whole sky, patiently collecting these faint, fierce flickers of the most energetic light in the universe, building up a picture of a sky we'd never properly seen before. And when Finkbeiner and his colleagues looked carefully at that picture, when they cleaned away all the ordinary glow, all the familiar light from stars and gas scattered across the galaxy, and asked what was left over, what was unexpected, what didn't fit, there they were. Two enormous lobes, two great bubbles of gamma-ray light ballooning up and down out of the very center of the Milky Way, one above the disk of the galaxy and one below, almost perfectly symmetrical, like a pair of soap bubbles caught mid-blow. Together they stretch about 50 degrees across the sky. Now 50 degrees is a lot. Hold your hand out at arm's length, fingers spread wide. The span from your thumb tip to your little finger covers roughly 20 degrees of sky. These bubbles stretch across more than two of those spans. They are simply gigantic, a structure that, if your eyes could only see it, would dominate half the sky, arching over and under the soft river of the Milky Way like the wings of something impossibly large. These came to be called the Fermi bubbles after the telescope that found them. Sit with that for a moment. In the quiet. There has been, this whole time, a structure tens of thousands of light years tall, hanging in the sky above us, and we walked beneath it for our entire history without ever knowing. Every astronomer who ever lived, every shepherd who ever traced the stars, every sailor who ever steered by them, none of them saw the bubbles. They were always there. We just hadn't built the eyes yet. And that on its own would be a wonderful thing. But the story doesn't stop there, because some years later, in 2020, a second telescope looked at the same patch of sky in a different kind of light and found something even larger. This telescope is called eROSITA, and it rides aboard a spacecraft named Spektr-RG out in the dark beyond the Earth. Where Fermi watches the sky in gamma rays, eROSITA watches in X-rays. X-rays are also a kind of high-energy light invisible to our eyes. You might know them best from a doctor's office, the way they slip through soft skin to show the bone beneath. The same kind of light, streaming across the universe, can be caught by a telescope built to receive it. And when eROSITA mapped the sky in X-rays, it found two bubbles too. But these were bigger, far bigger. The X-ray bubbles enveloped the gamma-ray ones completely, wrapped around them like a larger shell around a smaller one, reaching up and down perhaps 45 or even 50,000 light-years from the galactic center. Nearly the full height of the galaxy itself, top to bottom. An almost unthinkably large structure painted across the sky in light we'd only just learned to see. These are the eROSITA bubbles, and here's the part that makes an astronomer's heart beat a little faster, even at this gentle hour. The two sets of bubbles, the gamma-ray ones and the bigger X-ray ones, they share the same center, the same shape, the same hourglass form, narrow at the galactic core and ballooning outward above and below. They line up. And when two completely different telescopes watching two completely different kinds of light both find the same enormous shape pointing back at the same single spot, well, that's the universe telling you as clearly as it can that something happened there, something at that center, poured out a staggering amount of energy, and these bubbles are what it left behind, the smoke, if you like, that's still drifting upward and outward from a fire that burned long ago. So now we have our shape in the sky. And we have a place it all points to, the center of the Milky Way, the dynamical heart of our galaxy, the still point that the whole great spinning pinwheel of 400 billion stars turns around. And it's time, gently, to tell you what lives there. At the very center of our galaxy, 26,000 light-years away from where you're lying right now, sits a black hole. Its name is Sagittarius A star, written with the letters Sgr, then a capital A, then a little asterisk, that star-shaped mark. And astronomers usually just say Sagittarius A star, or Sgr A star for short. It sits in the direction of the constellation Sagittarius, which is where the name comes from, and on a clear summer night in the southern sky, you can actually look toward it, more or less. Though of course you can't see the black hole itself. You're just looking toward the thick, glowing heart of our galaxy, all those crowded stars, and somewhere behind and within all that light, hidden, patient, sits this thing. And it is not small. Sagittarius A star has a mass of about 4.1 million suns. Let me say that again, slowly, because the number is so large it slides right off the mind if you say it too fast. 4 million times the mass of our sun. Take our sun, that enormous ball of fire, so vast that more than 1 million Earths would fit inside it, so heavy it holds every planet in our solar system on its leash, across billions of miles of empty space. Take that and imagine 4 million of them. Now crush all of that down, all 4 million suns worth of stuff, into a single point so dense, so deeply collapsed, that not even light can climb back out of its gravity. That's what sits at our galaxy's center, that Sagittarius A star. Now here is where the gentle mystery begins. Here is the strange, lovely puzzle I want to lay in your lap tonight and let you turn over slowly as you drift. You'd think, wouldn't you, that a black hole 4 million times the mass of the sun, sitting at the center of a galaxy crowded with stars and gas and dust, would be a monster, a devourer, a roaring, blazing furnace swallowing everything around it, shining like a beacon you could spot clear across the universe. That's certainly the picture most people carry around in their heads when they hear the words black hole. Something hungry, something violent, the cosmic drain at the bottom of everything, sucking in all it can reach. But Sagittarius A star is nothing like that. Not now. Right now, tonight, as you lie here, the black hole at the center of our galaxy is one of the quietest, calmest, most peaceful giants you could ever imagine. It is barely eating at all. How little is it eating? Well, picture this. That whole 4 million sun black hole, that vast gravitational well at the heart of the galaxy, is currently swallowing only about an asteroid's worth of material per day. A single asteroid, a cosmic crumb, a little drifting rock and gas here and there falling in, out of an entire galaxy's worth of stuff swirling around it. This enormous thing is sipping the tiniest amount, like a person at a great banquet table who takes one small bite and then simply sits, hands folded, content. And here's the part that's almost hard to believe. Even most of the little that does fall toward it never makes it in. A great deal of the material that starts falling towards Sagittarius A star gets flung back out again before it ever reaches the point of no return, blown away, returned to the dark. The black hole turns away most of its own meal, and so it shines, but only barely. There's a kind of theoretical ceiling for how brightly a black hole of a given mass can shine when it's feeding at full tilt. Astronomers call it the Eddington luminosity, named after the astronomer Arthur Eddington, and you can think of it simply as the maximum brightness, the absolute top of the dial, the loudest a black hole of that size could possibly roar. Sagittarius A star right now is shining at about 1/billionth of that maximum, 1/billionth. Turn the dial all the way down, down past faint, past dim, past nearly off. That's where our black hole sits. If its full possible brightness were the blazing noonday sun, then what we actually see from it is fainter than the very last ember of a candle that's almost gone out. The merest red glow you'd have to lean close in a dark room to even notice. So that's our giant. 4 million suns of collapsed matter, and yet so faint, so still, so gently sipping, that for a long time we couldn't even be certain it was there at all. A sleeping giant, a great quiet thing at the center of everything, eating a crumb a day, dreaming if black holes can dream. And now you can feel the puzzle, can't you? Now you can feel the lovely contradiction that this whole night is built around, because we started up there in the sky with those two enormous bubbles, 50,000 light-years of structure burned across the heavens, two great lobes of fierce invisible light pouring up and down out of the galactic center. Clearly, unmistakably, the wreckage of something tremendous. Some vast outpouring of energy, some explosion, some eruption, some unimaginable burst that blew those bubbles outward like breath into a balloon. And yet here, at the very spot it all points back to, we find this. A quiet, sleeping, barely eating giant, shining a billionth of what it could, so calm it almost seems incapable of harming a thing. How can both of these be true at once? That's the mystery, that's the thread we're going to follow slowly and softly through the rest of this night. How can something we can't even see, something so dark and so still it took us decades just to confirm it exists, how can that same something have left a scar across half the sky? How does a giant this quiet, this gentle, this asleep, account for the most enormous structure in our galaxy hanging right above its head? There's only one answer that makes any sense. And it's the answer the whole rest of our story turns on, so let me say it gently and let it settle in. It wasn't always asleep. The giant is quiet now, but it has not always been quiet. Somewhere back in the deep past, long, long before any of us, before our cities, before our languages, before even our species had quite taken its present shape, this same sleeping thing at the center of our galaxy woke up. And when it woke, it didn't stir gently. It roared, it blazed. For a while, it became one of the brightest things in this entire corner of the universe, pouring out energy on a scale that's almost impossible to hold in the mind. And it was that ancient roar, that long-ago awakening that blew those bubbles up and out into the sky, where they still hang today, slowly fading, the cooling smoke of a fire that burned a very long time ago. The bubbles are a fossil. That's the way I'd like you to think of them as you drift. Not as something happening now, but as a trace, an imprint, a footprint left in stone. The way you might walk along an ancient shore and find, pressed into the rock, the perfect outline of a creature that died millions of years before the first human ever drew breath. And from that single shape in the stone, you could know that the creature had been there, how big it was, how it moved, even though you never saw it and never could. The bubbles are that footprint, only written in light instead of stone, and stretched across the whole sky. Something gigantic was here. Something woke and burned and went back to sleep. And it left this behind, and of course the moment you understand that, the moment you really feel it, a new question opens up beneath you, quiet and a little thrilling. If the giant is asleep now and woke once before, then could it wake again? Is it gone for good, this old fire, or is it merely banked, merely resting, merely waiting for the next thing to fall in and stir it back to life? We'll get there. I promise we'll get there, gently, before the night is through. But not yet. There's no rush. First, we have to do the patient, beautiful detective work. because that's really what all of this is. A piece of detective work spread across the sky and across millions of years. We're standing at a scene long after the act, reading the clues that were left behind, trying to reconstruct what happened from the marks it made. And it turns out the universe is a very honest witness if you only know how to read what it's written down. So let me promise you the shape of what's coming, and then we'll slow right down and begin properly. We're going to look at the evidence that this quiet giant truly did erupt, and not just guess at it, but really find the fingerprints, including a ribbon of gas far out beyond our galaxy that is still glowing tonight from a flash that happened so long ago that our distant ancestors were walking the Earth when the light first struck it. We're going to find out how, exactly, you weigh a thing you cannot see. How astronomers came to know that 4 million sun figure, not by guessing, but by watching, patiently, for decades, the way stars dance around the dark. We're going to talk about the extraordinary day in the spring of 2022 when humanity, for the very first time, actually photographed the shadow of this black hole, turned nearly the whole planet into a single great eye to do it. And we're going to come, at the very end, gently to that last question. Could it wake again? And if it did, so very far away, would we down here have anything at all to fear? But all of that is for later. For now, just rest with the picture we've drawn. 2 enormous bubbles in the sky, one reaching up, one reaching down, 25,000 light years each, painted in light our eyes were never built to see, found by patient telescopes floating high above the Earth. And at the point they grow from, the still, dark center of everything, a sleeping giant of 4 million suns, eating a crumb a day, shining a billionth of what it could, so quiet you'd never dream it had the power to scar the heavens. And yet it did. That's the thing we know, the scar is up there right now, so the only question left is how. How did something so still leave a mark so vast? How does a sleeping giant come to roar? Breathe slowly now. Let the number drift through your mind. 4 million suns crushed to a point, 26,000 light-years away, quiet as a held breath. Let the bubbles hang there in your imagination, enormous and silent, slowly fading in the dark. There's no need to hold any of it tightly. The ideas will keep. They've kept for millions of years already. They'll keep a little longer while you rest. We're going to find out what woke the giant. We're going to read the writing it left across the sky, and we'll do it slowly, softly, the way you do everything here. So let's begin, shall we? Let's start where the story really starts. Not with the bubbles themselves, but with the faint, far-off glow that finally let astronomers put a date on the night the center of our galaxy caught fire. There's a thread of gas out there, tens of thousands of light years away, that has been quietly shining for millions of years. And it's been waiting all this time to tell us exactly when the giant last awoke. Let me tell you about it. But before we follow that thread of gas, let me hold us here for just a moment longer, back at the place it all grows from, because the more you understand how still this giant truly is, the stranger the scar above it becomes. Picture the center of our galaxy, not the way it's usually drawn, all swirling fire and menace, but the way it actually is. There's a point there, a single point, and we call it Sagittarius A star. You might hear it written as Sgr A star, with a little asterisk where the word star would go. That asterisk has a sweet story behind it, and we'll get to it. For now, just hold the name, Sagittarius A star, the dark heart of the Milky Way. It sits about 26,000 light years from where you're lying right now. That's the distance light itself would travel, racing at its impossible speed for 26 100,000 years. The light leaving it tonight will not reach the Earth until long after everyone you've ever known is gone, and the light we see from it now left during the last ice age, when there was still ice across much of the world, and our ancestors were learning to survive it. So in a very real way, when we look at the center of our galaxy, we are looking into the deep past. We never see it as it is. We only ever see what it was. And what is it? It's a black hole. A region where so much matter has been crushed into so small a space that gravity folds in on itself, and nothing, not even light, can climb back out. The mass of this one is hard to even say out loud and have it mean anything. 4 million suns, a little more actually, around 4.1 million times the mass of our own sun, all of it gathered into a point you could never see, never touch, never approach and return from. Now here's the part that should surprise you. Here's the quiet little paradox I want you to carry into sleep tonight. You'd expect a thing like that to be ravenous. 4 million suns of gravity sitting in the busiest, most crowded corner of the galaxy, surrounded by gas and dust and stars packed close together. You'd expect it to be tearing the neighborhood apart, swallowing everything within reach, blazing like a furnace. It isn't. It's barely eating at all. Right now, tonight, as you settle deeper into your pillow, Sagittarius A star is consuming only a trickle of material. The astronomers who measure these things put it at something like 1 asteroid's worth a day. Imagine that, a black hole of 4 million suns, and its entire daily meal is a single drifting rock, the kind that wanders harmlessly through our own solar system all the time. It picks at its food, it nibbles, and most of what does fall toward it never even makes it all the way down. The hole flings the majority of it back out into the dark before it ever crosses the threshold of no return. It's a fussy eater, a reluctant one. There's a way scientists measure just how dim a black hole is, and it has a lovely name: the Eddington luminosity. Think of it as a kind of speed limit for brightness, the absolute maximum a thing of a given mass could ever shine if it were feeding as hard as physics allows. Sagittarius. A star is shining at roughly 1/billionth of that limit. 1/billionth. If the maximum it could blaze were the full noon sun, what we actually see from it would be fainter than the faintest star you've ever squinted to find on a clear night. A pilot light, a single ember left glowing in a hearth that's gone cold. So that's our giant. Enormous, beyond imagining, and gentle as a sleeping animal. So quiet that for a long time we couldn't be sure it was there at all. And that gentleness is exactly what makes the scar above it so impossible. Because something burned those 2 great bubbles into the sky. Something poured energy out of that still center with such force that it punched lobes of glowing gas 25,000 light-years up and 25,000 light-years down, perpendicular to the flat plate of the galaxy, like an hourglass laid against the dark. A man named Doug Finkbeiner and his colleagues found them in the year 2010, hidden in the gamma-ray light gathered by a telescope orbiting our planet called the Fermi Gamma-ray Space Telescope. Gamma rays. The most energetic light there is, the kind released only when something truly violent has happened. We can't see gamma rays with our eyes. We had to build an instrument and lift it above the air to catch them. And when we finally did, there they were. 2 vast bubbles glowing in a light we were never built to perceive, sitting silently above and below the very center that does nothing now but nibble at asteroids. They are so large that if your eyes could see them, they wouldn't fit in your gaze. They sprawl across some 50 degrees of the sky, each one. Hold your arm out and spread your fingers wide. That gap from thumb to little finger is about 20 degrees of sky. Now imagine more than twice that, glowing, arching over you, and another the same below your feet on the far side of the world. That's the size of the thing. A figure of 8, an hourglass, 50,000 light-years tall from top to bottom, centered on the sleeping giant. And here's where it gets stranger still, because the Fermi bubbles weren't even the whole of it. 10 years later, in 2020, another telescope looked at the same patch of sky in a different kind of light. This one was an X-ray telescope named eROSITA, riding on a spacecraft called Spektr-RG, far out in space. X-rays, like gamma rays, are invisible to us, another flavor of light too fierce for human eyes. And when eROSITA mapped the galactic center in X-rays, it found bubbles too, larger ones. A second pair of lobes, even bigger than Finkbeiner's, wrapping around the Fermi bubbles like a larger shell around a smaller one. Two telescopes, two completely different kinds of light, two independent looks at the same dark heart. And both of them found the same thing, the same Sgr written twice in two hands, saying the same word. That's important. When two separate instruments measuring two separate kinds of energy both stumble onto the same enormous structure in the same place, you stop wondering whether it's a trick of the data. It's real, it's up there, something happened. So now sit with the full shape of the mystery, because this is the question the whole night turns on. We have a black hole so quiet it eats a single rock a day and glows a billionth of what it could. And we have a Sgr across half the visible sky, 50,000 light-years of glowing gas, that something at that exact center clearly blew outward with the force of a small galaxy waking up. Those two facts do not fit together. A sleeping giant does not carve mountains. A creature picking at crumbs does not leave a wound the size of the sky. How can something we can't even see leave a mark across half the heavens? That's the loop I want to leave open as you drift. Don't try to solve it. Just let it hang there, glowing softly in the back of your mind, the way the bubbles hang in the dark above the galaxy. We'll answer it. I promise we will. But the answer doesn't live in the bubbles themselves. The bubbles only tell us that it happened. They don't tell us when. For the when, we have to leave the center entirely. We have to travel far out, past the crowded core, past the spiral arms, out to a lonely ribbon of gas drifting near two small companion galaxies, far from everything. And that ribbon, faint and cold and almost forgotten, turns out to be the most patient witness in the whole story. It saw the giant wake, and it has been glowing with the memory of that light ever since, holding the date for us, waiting for someone clever enough to read it. So let's go to it now slowly, the way we go everywhere here. Let's follow the faint glow out into the dark and see what it remembers. The ribbon has a name. It is called the Magellanic Stream, and if you could step outside the Milky Way for a moment, float above it, the way you might hover above a city from a great height, and look down at the lights, you would see it as a long, faint smear of gas, trailing behind two small, irregular galaxies, the large Magellanic Cloud and the small Magellanic Cloud, like a scarf pulled loose and left drifting behind someone who moved through the room too quickly. It stretches across an enormous span of sky, this ribbon. It is one of the largest structures associated with our galaxy's neighborhood, and for a long time, astronomers regarded it mostly as a curiosity, a byproduct of gravitational tides, the Milky Way's gravity gently pulling at those two small companions and drawing a thread of their gas out behind them as they orbited. That's a reasonable explanation. Tidal stripping is a real and well-understood process. Galaxies do pull material from their neighbors. The Magellanic Stream looked like a perfectly ordinary example of that, and so it sat in catalogues and sky surveys, noted and filed away, not particularly remarkable beyond its size. But there is a section of it that is not ordinary. There is a bright patch, a region of the stream that glows more strongly than the surrounding gas, that shows a level of ionization, atoms with electrons stripped away, charged and energized, that cannot be explained by any of the usual sources, not by the ultraviolet light of ordinary stars, not by the gentle background radiation that fills the universe, not by any realistic combination of known local sources. The gas there is too hot, too thoroughly ionized, too bright in the wrong ways for anything nearby to account for it. This is the kind of anomaly that sits in data for years before someone asks the right question. And the right question, when it finally came, was simple and quiet and rather extraordinary. What if the ionization isn't coming from anything nearby? What if it was produced by a source that is no longer active, a source that switched on, blazed and switched off, but left the gas illuminated the way a lighthouse beam might sweep past a distant fog bank and leave a glow that persists after the light has moved on? The person who followed that question most carefully was an astronomer named Joss Bland-Hawthorn, and the source he eventually pointed to was Sagittarius A itself. The logic, once you see it, has a kind of beautiful simplicity, the kind of simplicity that only appears after years of careful, painstaking elimination. Let's walk through it slowly. The Magellanic Stream sits at an enormous distance from the galactic center, well above and below the plane of the Milky Way's disk, out in what astronomers call the halo. If you want to ionize gas at that distance, you need a source of radiation powerful enough to reach that far. Most things in the galaxy cannot do that. The combined light of hundreds of billions of stars in the galactic disk is powerful, but it is also largely absorbed and scattered by the gas and dust of the disk itself before it can escape into the halo in sufficient quantities. Ordinary stars don't do it. Supernovae, as violent as they are too brief and too scattered to account for sustained ionization at that range. But a sufficiently bright active galactic nucleus, a black hole accreting at a high rate, blazing like a quasar or a Seyfert galaxy, that is a different thing entirely. An AGN at the center of the Milky Way firing radiation outward along the polar axis, perpendicular to the disk, could punch through the thinner gas above and below and reach the stream. The geometry works. The galactic center sits roughly in the right direction from the illuminated patch. The type of ionization matches what you'd expect from a particular spectrum of radiation. Bland-Hawthorn and his colleagues, working from observations published in 2013 and refined in later work through 2019, did the calculation. They asked what kind of event at Sagittarius A with what luminosity, for what duration, aimed in roughly what direction, could produce the ionization pattern we see in the Magellanic Stream today. And the answer that came back was specific and startling and carries a date. The flare would need to have been a Seyfert-level event. Seyfert galaxies are a class of active galactic nuclei, not the most violent, not quasars blasting across the universe at peak fury, but powerful, sustained, luminous in ways that dwarf anything we see from Sagittarius A today. During this event, Sgr A would have been somewhere between roughly 100,000 and 1 million times brighter than it is right now. Not a brief flicker of the kind it still produces on a daily basis. Those are modest, minutes to hours, brightening events. This would have been a sustained, blazing period of activity, burning at something approaching a genuine active galactic nucleus, lasting perhaps as long as 300,000 years. 300,000 years is a long time by human reckoning. It is longer than our entire species, Homo sapiens, has existed, and yet in galactic terms it is brief, a single deep breath. The timing that best fits the data places this event at roughly 3.5 million years ago. That number has uncertainty attached to it. It is not the way you'd give a birthday, not a fixed point, but a range, the most probable value within a spread of perhaps 2 to 6 million years, with the clustering of evidence tending to favor the lower end of that range, somewhere in the neighborhood of 3 to 4 million years. The physics of light travel, of ionization decay rates, of how gas remembers and then forgets a burst of radiation, these are the tools used to work backward to that date. It is forensic calculation, not direct measurement. But it is careful, grounded science, and the result is consistent across multiple lines of evidence. 3.5 million years ago, sit with that for a moment, let it settle. 3.5 million years ago, the center of our galaxy, this same quiet, dark, slow-feeding object whose shadow we would eventually photograph in 2022, was blazing. It had become, briefly, a thing recognizable to any astronomer studying distant active galaxies. Not the most powerful event in the universe, but powerful enough. A Seyfert-level nucleus burning in the core of the Milky Way, sending twin beams of radiation outward along the poles, lighting up gas tens of thousands of light-years away. And on the ground, far below that light, something was walking. The genus Australopithecus was alive 3.5 million years ago. This is the same era as Australopithecus afarensis, the species we know best from a skeleton found in Ethiopia in 1974, a small, upright walking hominin nicknamed Lucy. Her bones dated to roughly 3.2 million years. Lucy and her kind walked on two legs across the grasslands and woodland edges of East Africa. They were not us. They would not meet the definition of Homo, our own genus, for another million or more years. But they were recognizably ours. Something in their posture, in the shape of their feet and hips, in the way they moved through the landscape, marks them as part of the lineage that eventually produced you listening here, in whatever quiet place you found tonight. They did not have language. They almost certainly had no concept of the sky as anything other than weather and daylight and the comforting dark of night. Whatever the galactic center was doing above them would have been invisible to them in any meaningful sense. The Milky Way itself, and that faint band of light across the night which we now know is our galaxy, seen edge on from inside, they may have seen on clear moonless nights as their successors would for millions of years. They had no way of knowing what lay at its center. They had no way of knowing that the center had recently, in galactic terms, let out a roar. And yet there is a question worth sitting with, even if we can't answer it, even if the honest answer is probably nothing dramatic. The radiation from a Seyfert-level flare in our galactic center, propagating outward along the polar axis above and below the disk, would not travel harmlessly through absolute vacuum before reaching the gas it ionized. Our solar system, 4.5 billion years old, sitting about 26,000 light-years from the center in the plane of the galactic disk, not above it or below it, would have been largely shielded by the disk itself, by the gas and dust that absorbs radiation in the plane. The most intense ionizing radiation appears to have been directed preferentially perpendicular to the disk, upward and downward into the halo, not outward, through the disk, in the directions where populated stellar systems like ours sit. What the sky may or may not have looked like from the surface of Earth, or from the forests of East Africa where Australopithecus walked, is genuinely uncertain. Some speculative discussions suggest there might have been a faint enhancement in the sky, a very slight brightening at the galactic center, perhaps visible under exceptionally dark skies. But this is inference, stacked on inference, and honesty requires us to hold it gently. What the evidence actually records is the effect on distant, highly exposed gas in the halo, gas that had nothing between it and the source. What was visible from a planetary surface is a different and much harder question, and the answer is likely much less dramatic than imagination might prefer. What we can say is this: 3.5 million years ago, this thing happened. The center of our galaxy came alive in a way it has not been alive since. Something fell toward Sagittarius A. Some accumulation of gas, perhaps, some portion of material that finally lost enough angular momentum to tumble inward past the last stable orbit, past the point where physics allows it to stop and think. And the black hole fed, really fed, not the trickle it manages today, a flood or something much closer to one. And the evidence for that event is not gone, it is still here. It is written in gas, it is glowing quietly in a ribbon of material trailing behind two small galaxies on the far side of the Milky Way's halo, and the pattern of that glow, the specific fingerprint of ionized hydrogen and oxygen, the exact temperature and intensity of the emission, points back like a long, faint arrow to the center, and to a moment that our most careful calculations place at roughly 3.5 million years in the past. The Magellanic Stream is the most distant and patient witness we have found, but it is not the only one. There is another echo, and this one is closer, much closer, and much more recent. If the Magellanic Stream tells us about a roar from millions of years ago, there is a separate body of evidence suggesting that Sagittarius A had a smaller, shorter, more modest outburst. Not a Seyfert-level event, not something you'd see across tens of thousands of light years, but a burst that was still far beyond anything we observe from it today, within the last few thousand years. Perhaps as recently as 300 years ago. The evidence for this comes from a different kind of forensic observation, not ionized gas in the halo, but reflected X-rays. Scattered among the dense clouds of the galactic center region, there are enormous clouds of molecular gas, cold, dense, mostly hydrogen and other molecules, the raw material of future stars. One of the largest and best studied of these is known as Sagittarius B2, or Sgr B2, a massive cloud sitting about 300 light-years from Sagittarius A mice in the central region of the galaxy. Now, X-ray light travels in straight lines like all light, and if a source of X-rays flares brightly, some of that X-ray radiation will travel outward in all directions. Most of it will travel past any nearby cloud and keep going forever, lost in the vast empty dark. But some portion of it will strike the cloud, and a small fraction of that will scatter, the way a beam of light scatters off a mirror, or the way sound echoes off a cliff face. And that scattered fraction will be deflected into new directions, some of those directions pointing toward us, arriving at our telescopes later than the original burst would have, delayed by the extra path length of the detour. This is an X-ray light echo, and it is precisely what has been observed from Sgr B2. When astronomers, using observations that included the Chandra X-ray Observatory, whose images gave us the clearest pictures of the galactic center region, studied the molecular clouds near Sagittarius AD, they found that several of those clouds were glowing in X-rays, not from any internal source, not from background radiation, but from reflected, echoed X-ray emission that matched, in its spectrum and its intensity, what you would expect from a burst of X-ray radiation originating at the position of Sagittarius A itself. The geometry of the reflection combined with the geometry of the cloud's position relative to the source and to us allows you to calculate when the original burst must have occurred. The extra path length taken by the reflected light, going from the source to the cloud to us, instead of directly from source to us, introduces a time delay that depends on the angles and distances involved. A 2013 study worked through this calculation and found something striking. The brightness of the X-ray reflection in Sgr B2 and the apparent fading of that reflection over the years that astronomers had been watching it was consistent with Sagittarius A having been dramatically brighter, perhaps 10,000 to 1,000,000 times brighter than today. Not millions of years ago, but within the last few hundred years. Some estimates place the peak of this smaller, more recent outburst around 300 to 400 years ago. The X-ray echo we are watching now, bouncing off the molecular clouds, is arriving at our telescopes because the original burst's light hit those clouds and scattered back toward us, and we are catching that scattered reflection in the centuries after the flash. Think of it this way. Imagine you are standing in a dark room. Someone on the far side of the room strikes a match, briefly, just for a second, and then puts it out. You might not see the match itself, but you might, if the timing is right and the room's walls are reflective enough, see the brief gleam caught in the far corner of the room, arriving at your eyes a fraction of a second after the match went out, because the light had to travel to the corner and back. The molecular clouds around Sagittarius A are that corner, and we are watching the gleam. This doesn't change the fundamental picture of Sgr A as a quiet, underluminous, underfed black hole. But it adds texture to that quietness. It suggests that even the relatively recent past may not have been as still as today. 300 years ago, if the reconstruction is correct, something caused a brief surge. The hole flared perhaps for months, perhaps for years. We don't have the precision to say. And those X-rays raced outward in all directions, and the ones that struck the cold gas of Sgr B2 scattered, and some of those scattered X-rays are only now completing their longer journey and arriving at Earth. We are, in a very real sense, receiving a postcard from a different era of our galaxy's center, stamped and sent a few hundred years ago and arriving only now. And this gives us something important. It gives us a sense of range. We now have evidence of activity at two very different timescales. The vast Seyfert-level event that lit the Magellanic stream 3.5 million years ago, and this smaller, much more recent flickering captured in the X-ray echo from Sgr B2. Both point in the same direction. Sagittarius A is not merely capable of activity, it engages in activity on different scales at different intensities, separated by different intervals of relative quiet. The current quiet is not necessarily permanent. It has not always been this way, and there is no fundamental physical law that says it must remain this way. Let's stay with the timeline for a moment, because the numbers involved deserve a bit more attention, not to overwhelm, but because the sense of scale is part of what makes this story feel the way it does. That combination of strangeness and weight that is the whole reason we're here, drifting through it slowly in the dark. The Fermi bubbles, discovered in 2010, extend about 25,000 light-years above and below the galactic plane. To fill those bubbles, to inflate them with energetic particles and radiation to the levels we observe, required an enormous input of energy. The estimates for that energy are in the range of 10 to the 56th power ergs. That is written in scientific notation, 10 with 56 zeros after it, in the unit of energy called an ARG, which is itself a very small unit. 1 erg is roughly the energy of a mosquito in flight. 10 to the 56th of them is not a small number by any human measure. To put it in context, a typical supernova, when a massive star explodes at the end of its life, releases roughly 10 to the 51st ergs of energy. That is already a number that staggers ordinary intuition. A single stellar explosion outshines everything else in its entire galaxy for weeks, and the bubbles required the equivalent of somewhere between tens of thousands and hundreds of thousands of supernova explosions, all concentrated in the central region of the galaxy, probably over a period of millions of years, or in a single sustained active episode, or possibly both. This is not idle theorizing. The eROSITA bubbles, discovered in 2020 from data taken by the eROSITA instrument on the Spektr-RG spacecraft, are even larger than the Fermi bubbles. Where the Fermi bubbles extend roughly 25,000 light-years on each side in gamma rays, the eROSITA bubbles, observed in X-rays, extend further still, up to roughly 45,000 to 50,000 light-years on each side, enveloping the Fermi bubbles like a larger shell around a smaller one. Two independently operating instruments measuring two different forms of electromagnetic radiation, both finding enormous paired lobes centered on the same point. The interpretation that fits this most cleanly, not the only possible interpretation, but the one that accounts for both structures and their shared geometry and their shared axis, is a single massive energy injection from the galactic center. Perhaps a sustained period of elevated accretion onto Sagittarius A. Perhaps a combination of that plus the concentrated star formation and supernovae that we know have happened in the galactic center region over the past several million years. The debate about the precise mechanism is ongoing. What is not debated is the scale and the likely origin. Something happened at our galaxy's center, something large, something that left its mark not just in the immediate neighborhood of the black hole, not just in the central few light years, but across a structure that if you placed it in the night sky where you could see it with your eyes, would span more than half the visible sky. 50 degrees from top to bottom of the Fermi bubbles alone, in a sky where the full moon spans half a degree. We cannot see the Fermi bubbles with naked eyes because they glow in gamma rays and X-rays, forms of light our eyes are not built to detect. But they are there. They have been there. They have been drifting slowly outward from the center for millions of years, thinning and cooling as they go, carrying within their structure the encoded memory of whatever happened when they were formed. And back at the center, the thing that formed them sits, quiet, patient, eating its asteroid a day. The contrast is, when you sit with it, genuinely difficult to reconcile. It's the kind of thing that makes you want to check the numbers again, to make sure someone hasn't made an error. But the numbers have been checked many times by many independent teams with many different instruments and methodologies. The quiet is real, the Sgr is real, both are documented. There is something almost personal about this if you let yourself feel it. The Magellanic stream received that blast of ionizing radiation from our galactic center and began glowing around 3.5 million years ago. The light from that flare that went outward toward the stream, traveling at the speed of light, 300,000 kilometers per second, the fastest speed anything can travel in this universe, took roughly the travel time from our galactic center to the stream to arrive. Many tens of thousands of years, depending on the geometry. It has been glowing since. And 3.5 million years ago, on a small planet orbiting a middling yellow star, in the outer regions of the same galaxy, in a region shielded by gas and dust and the geometry of the disk, small creatures walked. They did not look up and think about X-rays. They did not notice the center of the galaxy becoming briefly active. They lived their short lives, walked their grasslands, and did not know. But we know because we kept looking, because people like Joss Bland-Hawthorn spent years working carefully through the math of what could and couldn't explain the light in that distant ribbon of gas. Because instruments like the Fermi Gamma Ray Space Telescope were built and launched and pointed at the sky, and because someone, Doug Finkbeiner and his colleagues in 2010, recognized in the data a pattern that shouldn't have been there and followed it until they understood what they were seeing. The bubbles did not announce themselves. The echo in the Magellanic stream did not come with an explanation attached. All of it had to be read the way you read a long, cold crime scene, assembling from fragments and traces and shadows the shape of something that happened long before anyone thought to look. There's a particular quality to this kind of science that is worth dwelling in for a moment, because it is at the heart of what makes this story something more than a list of facts. These astronomers were not there. They could not travel back 3.5 million years and observe directly. They had no recording, no photograph, no witness who saw the flare and wrote it down. All they had, all they ever have, is the present. Light arriving now. instruments sensitive enough to detect it, mathematical tools for reasoning backward from effects to causes, and yet they can tell you with genuine quantitative confidence that something happened, that the light from that something, still echoing in distant gas, is measurable, that the energy involved was at least in this range, that the timing was roughly that many million years ago within a spread of uncertainty that science acknowledges openly rather than hiding. This is what it means to do forensic astronomy. The universe leaves traces, and the patient work of reading those traces is how we come to know a past that no one living has ever seen. Now, there is a question that might be settling into your mind as you drift with all of this, a practical question, a human question. We've established that this happened. We've established the scale, bubbles, echoes, a blast from the era of Lucy and her kind. We've talked about the two time scales, the ancient roar and the more recent flicker. And the question that naturally follows is the one the title of this video quietly promises to answer. Could it happen again? We'll get to that. We will. The whole machinery of what triggers activity, or what it would take to feed this particular black hole, what's happening right now in its vicinity, what the observatories are watching, that is coming. But before we go there, we need to do something that might seem like a digression but is not. We need to understand exactly what we're talking about when we say Sagittarius A base. Not in the abstract. We've been building that, but concretely, measurably, with real numbers attached. Because the story of the flare, and the story of the quiet that followed it, and the story of what might end that quiet all depend on understanding just how massive this thing is, just how far away it sits, and just how we know any of that, given that we cannot see it directly. We cannot point a telescope at Sagittarius A the way we can point one at a star or a planet. A black hole, by definition, emits no light of its own. The event horizon, the boundary within which gravity is so strong that not even light can escape, is exactly that. A boundary of no return, a surface from which no information can reach us. Whatever falls across that line is gone from the observable universe. And yet we know its mass, we know it with extraordinary precision. We have a number to roughly 4.1 to 4.3 million times the mass of our Sun, with current best estimates converging near 4.15 million solar masses. That is not a guess or a rough order of magnitude estimate, but a real measurement, subject to refinement as techniques improve, arrived at through one of the most elegant applications of physics that the field of astronomy has ever produced. How? You cannot weigh something you cannot see, but you can watch what the invisible thing does to the things around it that you can see. And what it does is make them move. And the way they move tells you everything. This is at its heart the same logic Newton used when he looked at the motion of the moon and understood that the Earth must have a particular mass to keep the moon in its orbit at that speed and distance. The moon doesn't orbit nothing. The moon doesn't move in a circle because circles are pretty. The moon moves the way it does because a massive object, Earth, is sitting at the center of that motion and bending the moon's path with its gravity. At the center of our galaxy, there are stars. Not just stars in the loose general sense of the word, not the slowly drifting background populations that fill the disk and the halo of the Milky Way, moving with the calm, unhurried rhythm of a vast gravitational system in approximate equilibrium. These are stars that move the way nothing in the ordinary galaxy moves. These are stars that are doing something extraordinary. They are orbiting, not slowly, not in the wide, lazy ellipses that planets carve around distant suns, but tightly, ferociously. In orbits so compressed, so steeply curved, that watching them over years and decades looks less like observing a natural phenomenon and more like watching the hands of a clock sweep around a face. Except the clock is 26,000 light years away, and the face is drawn by gravity alone around an invisible point. This collection of stars is called the S-star cluster, and one member of that cluster, a star designated S2, sometimes written Sgr A, depending on which team named it, has become perhaps the most important single star in all of observational astrophysics, not because of what it is, because of what it does and what its motion tells us. S2 is not unusual in itself. It is a young blue star, probably a few million years old, maybe 15 to 20 times the mass of our Sun. Under ordinary circumstances, where if you transplanted it to the neighborhood of our solar system, if you encountered it drifting through the galaxy like a normal star, it would be unremarkable. An ordinary blue star among 100 billion others. But S2 is not in ordinary circumstances. S2 is locked in an orbit around Sagittarius A, and that orbit is breathtaking. Take a moment to settle into this wherever you are. If you have a blanket nearby, pull it a little closer. This is one of those places in the story where the numbers, if you let them wash over you without rushing, do something to the way the night feels. S2 completes one full orbit around the galactic center in roughly 16 years. 16 years. That is a time scale a human being can hold in their hands. Children born in 1 year of S2's orbit are in their mid-teens by the time S2 has come around again. Astronomers who began observing it early in their careers have watched it complete multiple circuits. It is not a geological timescale or a cosmological one. It is a human timescale. And that is part of what makes it so powerful as a measurement tool. At the closest point of its orbit, the point called perihelion, the moment when S2 swings nearest to Sgr A, it comes within approximately 17 light hours of the black hole's center. 17 light hours. That is roughly 120 astronomical units, about 120 times the distance from the Earth to the Sun, which sounds large until you remember that we are talking about a star that is orbiting the most massive, compact object in the entire Milky Way. At that closest approach, the space around S2 is warped in ways that have no equivalent anywhere in the ordinary solar neighborhood, and at that perihelion, S2 is moving at approximately 7,650 kilometers per second. Let that number breathe for a moment. 7,650 kilometers every second. That is roughly 2.5% of the speed of light. It is fast enough that the effects of Einstein's general theory of relativity, the bending of space-time, the slowing of clocks in deep gravitational wells, the shift of light toward the red as it climbs out of gravity, are not theoretical corrections that can be ignored. They are measurable. They have been measured. S2's orbit is not just a Newtonian gravitational problem. It is a laboratory for testing the extremes of relativistic physics, sitting right there at the center of the galaxy, visible to anyone with a sufficiently powerful telescope and enough patience. And patience is exactly what the story requires next. Two teams working independently on opposite sides of the Earth in terms of institutional culture and approach decided in the early 1990s to do something that had almost never been done in astronomy at that scale: to commit to watching the same patch of sky night after night, year after year, for decades. Not because a single observation would tell them anything definitive, but because the signal they were looking for was only visible in time. You cannot see an orbit from a single photograph any more than you can understand the Earth's seasons from a single afternoon. One team was led by Reinhard Genzel, working with the Very Large Telescope, the VLT, operated by the European Southern Observatory in the Atacama Desert of Chile, one of the driest and highest places on Earth, where the atmosphere is thin enough and still enough that the seeing is extraordinary. Genzel is a German astrophysicist, and his group at the Max Planck Institute for Extraterrestrial Physics in Garching became the heart of a European effort to map the motions of stars near the galactic center over the very long haul. The other team was led by Andrea Ghez, working primarily with the Keck Observatory on Mauna Kea in Hawaii. Twin 10-meter mirrors perched on an ancient volcanic summit at about 4,000 meters elevation, so high that the air above carries less than half the water vapor of sea level, making it ideal for the kind of infrared astronomy needed to peer through the dense dust clouds that otherwise obscure the galactic center from visible light telescopes. Both teams used adaptive optics, a technology that corrects in real time for the atmospheric blurring that smears starlight before it reaches the detector, essentially reading the distortion introduced by the atmosphere many times per second and flexing a deformable mirror to cancel it out, recovering the sharpness that would otherwise be lost. Without adaptive optics, the stars near the galactic center blur into an indistinguishable smear. With it, individual stars separated by fractions of an arcsecond can be tracked as distinct points. Over the following decades, through the 1990s into the 2000s into the 2010s, both teams mapped the positions of dozens of stars in the S-star cluster with steadily improving precision. The stars moved. Year by year, their positions shifted in ways that, taken together, could only be explained by a single massive object at the center of the cluster, exerting gravitational force on everything around it. The more stars you tracked, the more precisely you could locate the center of force. The more orbits completed, the better constrained the mass of the central object became. S2 was the star that changed everything, because its orbit is the tightest and fastest of the well-characterized S-stars. When it swept through perihelion, when it made its closest approach and reached those dizzying speeds, the observations became extraordinarily sensitive to the enclosed mass, because that is precisely when the gravitational influence is most acute, when the orbit is most tightly curved, when the numbers are most demanding of accuracy. The result, refined over 30 years of careful observation, is that number approximately 4.1 to 4.3 million solar masses converging near 4.15 million, locked in a region of space so small that it must be a black hole. Nothing else, no cluster of dark stars, no compact collection of neutron stars, no exotic form of matter we have yet imagined, could squeeze that much mass into that small a volume and remain stable against gravitational collapse. The concentration is too extreme for any known alternative. In 2020, the Nobel Committee in Stockholm agreed that this was sufficiently important to recognize. The Nobel Prize in Physics that year went, in part, to Reinhard Genzel and Andrea Ghez, the first woman to receive the Nobel Prize in Physics since Maria Goeppert-Mayer in 1963, for the discovery of a supermassive compact object at the center of our galaxy. The prize was shared with Roger Penrose, who received his half for the separate but deeply related theoretical work of showing, through mathematical proof, that the formation of black holes is an inevitable consequence of general relativity. It is worth pausing here, in the quiet of wherever you're listening, to appreciate what that Nobel recognition really marks. Two teams independently watching the same invisible thing through different telescopes on different mountains in different hemispheres, arriving at the same answer over 30 years of patient observing. Science at its most methodical and most beautiful. Nobody was watching the black hole. They were watching the way it bent the fabric of motion around itself, the way a large stone under a blanket can be found by running your hand across the cloth and feeling the shape of what lies beneath. And in more recent years, the Genzel team's work at the VLT got even sharper. They deployed an instrument called gravity, a remarkable interferometric tool that combines the light from all four of the VLT's giant 8-meter mirrors as if they were a single telescope with a baseline of 130 meters, dramatically improving the resolving power. With gravity, it became possible to track S2's position with such precision that the orbit's relativistic effects, the precession of the orbit predicted by general relativity, the gravitational redshift as light climbs out of the black hole's gravity well, became directly detectable in the data. Not as marginal hints, as clear, unambiguous signals. Einstein's theory, tested at the Galactic center at the edge of a 4 million solar mass black hole with a star moving at 2.5% of the speed of light. It held. So by the time the year 2022 arrived, astronomers knew with confidence what was sitting at the center of the galaxy and how massive it was. What they had never actually seen was the thing itself. The black hole remained invisible to every instrument that had contributed to its measurement. Photographing darkness, it turns out, takes an entirely different kind of telescope. The idea had been around for decades, but the theoretical prediction that a black hole, even though it emits no light of its own, should cast a shadow. Not a shadow in the ordinary sense, the way a tree casts a shadow by blocking sunlight. A shadow in the sense that the black hole's gravity would bend and capture the light from a glowing ring of heated gas swirling around it in an accretion structure, and that at the center of that ring there would be a dark patch, the region from which light cannot escape, the event horizon and the space very close to it appearing dark against the bright background of the luminous gas surrounding it. This shadow would be small, extraordinarily small by the standards of observational astronomy. For Sagittarius A, the predicted angular size of the shadow, the apparent diameter it would present to a telescope on Earth, is approximately 52 microarc-seconds. A microarc-second is 1/millionth of one arc-second. A full circle is 360 degrees. Each degree contains 60 arc-minutes. Each arc-minute contains 60 arc-seconds, and one arc-second contains 1,000,000 micro-arc-seconds. So 52 micro-arc-seconds is a fantastically, almost incomprehensibly small angle. The comparison that the astronomers who worked on this love to use, and it is a good one because it anchors the abstraction in something real and slightly absurd, is this. Seeing the shadow of Sgr A from Earth is like photographing a donut sitting on the surface of the moon. Or if the moon feels too abstract, think of it this way. Imagine you are standing in Los Angeles on a clear day, looking east. You want to see a single grain of salt resting on a tabletop in New York City. Not a grain of sand, a grain of salt. That is roughly the angular scale. This is what the astronomers needed to resolve. No single telescope on Earth can do this. The largest single-dish radio telescopes ever built, instruments with apertures of hundreds of meters, fall short of this resolution by enormous margins. To achieve 52 micro-arc-seconds, you need not a bigger telescope but a different kind of telescope entirely. What you need is an Earth-sized telescope. This is not metaphor. This is the underlying idea of very long baseline interferometry, usually abbreviated VLBI. In radio astronomy, if you place two radio dishes anywhere on Earth and point them at the same source at precisely the same moment, recording the incoming radio waves with atomic clock precision, you can later combine those recordings in a computer and extract interference patterns between the two signals. Those patterns carry information equivalent to what a single telescope with a diameter equal to the distance between the two dishes would have recorded. The resolving power scales with the distance between the dishes. The larger that baseline, the finer the detail you can recover. Take that logic to its limit. Spread your dishes as far apart as the surface of the Earth allows, to Chile, to Hawaii, to the South Pole, to Spain, to Greenland, to the American Southwest, to the French Alps. Use every existing large radio telescope you can recruit. Synchronize them all with hydrogen maser atomic clocks precise enough to keep time to within a fraction of a nanosecond. Record everything simultaneously. And then, months later, in a computing cluster, combine all those streams of data and reconstruct the image. This is the Event Horizon Telescope. Not a telescope in any single physical location. a collaboration of radio observatories distributed across the globe, including ALMA, the Atacama Large Millimeter Submillimeter Array in Chile, one of the most sensitive radio observatories ever built. The South Pole Telescope, operating at the geographic bottom of the world, the Submillimeter Array on Mauna Kea, the Institut de Radioastronomie Millimétrique telescopes in Spain and France, the Greenland Telescope, the Large Millimeter Telescope in Mexico, and others. Individually, each of these is a powerful and important observatory. Together, synchronized, they form a single instrument with an effective aperture of roughly the diameter of the Earth, about 12,000 kilometers across, and a resolving power sufficient to see that donut on the Moon. The data volumes involved are staggering. Each telescope records the incoming radio waves, electromagnetic radiation at millimeter wavelengths, which can penetrate the dust clouds that block visible light from the galactic center, at rates that generate petabytes of raw data during an observing campaign. The Internet cannot move this data from telescope to telescope in any reasonable time. The solution, which has a certain charm if you think about it, is to physically ship the hard drives. Researchers at the South Pole have to wait for the Antarctic winter to end before their drives can be flown out on cargo planes. The data from the bottom of the world travels to the analysis center the slow way, the old-fashioned way, on a plane, in a box, handled by people. Once the data arrived at the correlating centers, at MIT Haystack Observatory and the Max Planck Institute for Radio Astronomy in Bonn, the computational work of combining it all, of extracting a coherent image from millions of interference measurements, of accounting for atmospheric delays and calibration errors, and the rotation of the Earth during the observations, took years of careful algorithmic development. Multiple independent imaging teams worked in parallel, each using different computational approaches to ensure that any features in the final image were real signal and not artifacts of the method. The first major result from the EHT, released in April 2019, was the image of the supermassive black hole at the center of the galaxy M87, a much more massive beast, 6.5 billion solar masses, in a galaxy 55 million light-years away. That image, the orange glowing ring with the dark central shadow, became one of the most recognized scientific images of the decade. But M87's black hole, despite its enormous mass, presents a larger apparent angular size than Sgr A because of how the angular size scales. A more massive object that is farther away, trading mass for distance in a way that happens to make it slightly easier to resolve. Sgr A was harder in a different way, a more immediate, more frustrating way, because Sgr A is not patient. Sgr A flickers. M87's black hole is surrounded by a slowly evolving accretion disk. On the timescale of an observing campaign, days to weeks, it barely changes. The image is steady enough that you can average many observations together without smearing the features. Sgr A is nothing like this. Even in its current quiescent state, even while barely eating, Sgr A flares and varies in brightness in the near-infrared and X-ray on timescales of minutes to hours. The structure of the material orbiting it changes. The brightness distribution around the ring shifts. What you see at one moment is not what you would see an hour later. For the EHT, observing a source that changes faster than the duration of an observation is a severe technical problem. You cannot simply add up all the data from a night of observing as if it were one long, stable exposure. You have to account for the variability. The imaging algorithms had to be adapted specifically for a dynamically evolving source, essentially reconstructing not just the structure of the ring, but the way that structure was changing during the observation. And yet, on May 12, 2022, the Event Horizon Telescope collaboration released it, the first direct image of Sagittarius A. A glowing ring, orange and gold and smudged by the limits of the instrument's resolution. At its center, exactly where the theory predicted it should be, a darker region, and the shadow, the silhouette of the event horizon, and the photon capture region around it, projected against the bright backdrop of superheated plasma. The shadow diameter is approximately 52 micro-arc seconds, consistent with a mass of roughly 4 million solar masses, consistent with everything the 30 years of stellar orbit measurements had already told us. The S-star orbits and the shadow image are independent measurements, completely different in method, requiring completely different instruments, and they converge on the same answer. A 4 million solar mass black hole, confirmed from two entirely different directions. The light captured in that 2022 image had left the galactic center approximately 26,000 years ago. It departed before the end of the last ice age. Before modern humans had begun to leave traces we now recognize as the seeds of complex civilization, before the cave paintings at Lascaux were made. This light traveled for 26,000 years across the galaxy, passed through the dust and gas of the interstellar medium at a millimeter wavelength, specifically chosen, because those wavelengths can slip through the dust that would block shorter wavelength light, arrived at radio observatories spread across the surface of the Earth, one of them perched on a frozen plateau at the literal South Pole. Got recorded, got shipped, got combined, got processed, and became a photograph of a shadow, the shadow of an object from which no light escapes, photographed by its absence. There is something quietly wonderful about that. And this is perhaps the right moment to go back a little further, to step back not 26,000 years, but closer to 50, to a February night in 1974 when two astronomers at the National Radio Astronomy Observatory, working with a telescope in Green Bank, West Virginia, noticed something unusual. The galactic center had been known as a region of intense radio emission for some time. The whole region, the Sagittarius A complex, as it is sometimes called, is dense with gas and ionized material and the signatures of furious stellar activity. There is a lot going on in the few hundred light-years around the center, but within that already complex environment, Bruce Balick and Robert Brown, identified a source that was unusually compact, unusually bright in radio, and unusually stable. A source that sat precisely at the dynamical center of the galaxy and showed properties consistent with something very small, very energetic, and very concentrated. Robert Brown, recounting the naming later, described adding the asterisk, the star symbol, after Sgr A because the source was, in his word, exciting. The asterisk was borrowed from spectroscopic notation, where an asterisk after an element symbol denotes an excited atomic state, an atom that has absorbed energy and is sitting in a high-energy configuration. In that sense, Sgr A was named as an excited entity, something unusual and energetic in a category of its own. That February 1974 identification was the moment we put a finger on it for the first time. We didn't know yet what it was with certainty. We didn't know its mass, we couldn't image its shadow, but we had a precise radio address for the thing at the center of the galaxy, and that address was the anchor point around which all of the later work, the decades of stellar orbits, the EHT campaign, the Nobel Prize, would organize itself. It took nearly 50 years from that February night to the 2022 image. 50 years from a bright dot on a radio map to a photograph of the shadow of a 4 million solar mass black hole. That is a long time, and it is also, in the context of astronomy as a discipline, not very long at all. We went from not knowing what that bright compact radio source was to holding an actual image of it within a single human career's span. There is a certain pleasure in sitting with both images side by side in the mind, if not on paper. The original 1974 radio map, a bright, compact point in the crowded Sagittarius region, and the 2022 EHT image, a fuzzy orange ring, the shadow clearly visible at its center, the culmination of an Earth-sized telescope and decades of work. same object. 50 years of human knowledge between them. So now we have a mass, we have an image, we have a name and a naming story, and a 1974 discovery that put a radio address to what turned out to be one of the most important objects in our cosmic neighborhood. And we have a picture of it, blurry by the standards of, say, a photograph of a nearby nebula, but crisp beyond anything that should have been possible given what we were trying to see. But here is the thing that neither the mass measurement nor the image alone can tell you. Neither of these achievements, as beautiful as they are, quite captures what Sagittarius A is like right now, on any given night, while you are lying there listening to this. Because the story is not over, the object is not static, it is not a piece of dead stone sitting inertly at the center of the galaxy, frozen in the pose captured by a Nobel Prize or a radio telescope image. It is a living, varying, complicated entity, quiet by the standards of its own history, quiet by the standards of what we know it can do, but not still. There is a pilot light burning at the center of the Milky Way. It flickers, and the question of whether, and when, and how that pilot light could become something far larger. That is where the story goes next. Every few hours, something happens at the center of the galaxy. Not something catastrophic, not something that would register as a news headline or light up the sky, something small by the standards of Sagittarius A, but something. The black hole brightens. It flares, briefly, intensely, held in X-rays and near-infrared light. Chandra X-ray Observatory has caught it. The gravity instrument, the same interferometric marvel that tracked S2's orbit in such exquisite detail, has watched it. In 2024 and 2025, the James Webb Space Telescope turned its extraordinary infrared sensitivity toward the galactic center and found something remarkable. Sagittarius A is essentially never fully quiet. It flares constantly at varying intensities, sometimes surging by a factor of tens, occasionally by a factor of over 100, for minutes to hours at a stretch. A low, persistent sparkle from a source we once might have described as dormant. Scientists call it variability. The practical picture is something closer to a campfire that occasionally sends a bright tongue of flame sideways before settling back to its usual low burn. The flame is real. The heat is real, the fire is never entirely out, which brings us at last to weighing it, too. Because before we can understand what the black hole is doing now or what it might do in the future, we have to understand how we know what it is at all. An invisible object 26,000 light-years away. How do you weigh something you cannot see, cannot reach, cannot probe with any instrument directly? You watch what orbits it. This is the elegant, almost absurdly simple logic at the heart of two of the most consequential observing campaigns in modern astronomy. Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, leading a team using the Very Large Telescope in the Chilean desert, the VLT, an array of 4 massive mirrors that together constitute one of the most powerful optical infrared instruments on the planet, and Andrea Ghez at UCLA, leading a parallel effort using the Keck Observatory on the summit of Mauna Kea in Hawaii, a dormant volcano that places the telescope above most of the Earth's obscuring atmosphere. 2 separate teams, 2 separate continents, the same target, the stars in the immediate vicinity of the galactic center. Those stars are the S-star cluster, they are called, orbit the central point in tight, fast ellipses. And among all of them, one star stands out. S2, also designated S Ursa 2 in Gez's catalogue, because the 2 teams initially developed their own naming conventions before the field settled into shared terminology. S2 is close enough to the central mass, and its orbit is short enough that both teams could watch it complete a full revolution. Not in a human lifetime of casual observation, not something you could see shift from year to year with the naked eye, but over roughly 16 years of careful, continuous, high-resolution imaging, the star traces out its full ellipse and returns to where it started. Let that sit for a moment. A star, completing an orbit around an invisible point in 16 years. For comparison, Earth completes its orbit around the Sun in 1 year at an average speed of about 30 kilometers per second. S2 completes its orbit in 16 years, yes, but that orbit takes it, at its closest approach, to within about 17 light-hours of Sagittarius A, roughly 120 astronomical units, about 3 times the distance from the Sun to Pluto. And at that perihelion point, that moment of closest approach, S2 is moving at approximately 7,650 kilometers per second, nearly 8,000 kilometers every single second, about 2.5% of the speed of light. If you were standing on S2 at perihelion and somehow survived the radiation environment and the gravitational tidal forces, neither of which you would be moving fast enough that the effects of special relativity would be measurably altering the light you emitted. The Genzel and Gez teams actually detected those effects. The gravitational redshift predicted by Einstein's general relativity, the relativistic transverse Doppler shift. These are not theoretical considerations for S2, they are measured phenomena. The star's motion is so extreme and the precision of the gravity instrument at the VLT is so fine that Einstein's equations are observable in the light arriving from a single star's orbit around a dark point. And from that orbit, from the shape of the ellipse, from the period, from the speed at perihelion, you apply Kepler's third law. The relationship between orbital period and the size of an orbit and the mass enclosed within it, the same relationship Johannes Kepler worked out in the early 17th century by watching planets move around the Sun. Applied now, 4 centuries later, to a star whipping around a black hole at the center of the Milky Way, the enclosed mass, and the mass that must be sitting inside that tight orbit to produce those numbers, works out to approximately 4.1 to 4.3 million solar masses. 4 million suns, compressed into a region smaller than the distance from the Sun to the nearest star. Invisible to every telescope except through the gravitational signature it imprints on everything around it. Both teams, Genzel's and Gez's, working independently for nearly 30 years, arrived at the same number. In 2020, the Nobel Committee in Stockholm awarded the Nobel Prize in Physics jointly to Reinhard Genzel and Andrea Ghez, alongside the mathematical physicist Roger Penrose, who had shown decades earlier that the formation of black holes is a robust prediction of general relativity, not a mathematical artifact or a theoretical curiosity. The citation for Genzel and Ghez was precise. For the discovery of a supermassive compact object at the center of our galaxy, not black hole. The committee chose its words carefully, as it tends to, but what sits at the center of our galaxy with the mass of 4 million suns and a radius smaller than our solar system's inner planets trace out is not a compact object that admits of many other interpretations. And then came the image, May 12, 2022, the Event Horizon Telescope collaboration, a network of radio observatories spanning the planet, synchronized by atomic clocks linked by the technique of very long baseline interferometry to form an effective aperture the size of Earth itself, released the first direct image of Sagittarius A. A glowing ring of orange and yellow light, the emission from superheated gas, orbiting the black hole at enormous speeds surrounding a dark central region. The shadow, the silhouette of the event horizon itself, the boundary beyond which no light escapes, visible not because we can see inside it, but because it is dark against the lit gas behind it. A hole in the light. The angular size of that shadow is about 52 microarc seconds, To understand how small that is, consider that 1 arcsecond is 1/3600th of a degree. A micro arcsecond is a millionth of that. Resolving 52 micro arcseconds is equivalent to resolving an object the size of a donut sitting on the surface of the Moon, seen from Earth. Or in another comparison that circulated in 2022, it is like being able to read a newspaper headline in New York while standing in Los Angeles. Except the newspaper is made of light and is 26,000 light-years away. The Event Horizon Telescope is not a single dish. You cannot point at it. It is a collaboration, a simultaneity, a coordinated act of observation involving radio observatories on multiple continents and including facilities like ALMA, the Atacama Large Millimeter Array, a cluster of 66 radio antennas in the high desert of northern Chile at an altitude of 5,000 meters, above much of the water vapor that would otherwise blur the signal, and the South Pole Telescope, buried in the Antarctic ice and cold beyond easy imagining, pointed at a sky that circles endlessly without setting in the months-long polar night. When all of these observe the same source simultaneously, and when the data are cross-correlated with extraordinary precision using the timestamps provided by hydrogen maser atomic clocks, accurate to better than a trillionth of a second, the effective resolution becomes that of an Earth-sized telescope. The data volumes are, by ordinary measures, staggering. The petabytes collected during an EHT observing run cannot be transmitted over any existing network in reasonable time. They are instead copied onto hard drives. Physical drives, the kind you might buy at an electronics store, just many thousands of them, and shipped by airplane from each facility to the correlation centers in Massachusetts and Bonn, where they are combined and processed. The image you may have seen, the glowing orange ring, is the result of that process. Petabytes of radio data gathered across a planet, flown across oceans, correlated and reconstructed into a picture of a shadow at the edge of space-time. And the light that made that image, the radio waves that arrived at those dishes, left Sagittarius A roughly 26,000 years ago, during the last ice age. When our ancestors were crossing land bridges and painting on cave walls and watching a night sky that already contained the same point of darkness at the galaxy's center, already sat above the same quiet, starving, flickering thing, and had no way of knowing it. We look at that image and see the black hole as it was during the Pleistocene. It seems worth pausing on that for a moment. Whatever you may feel about the nature of time and distance, there is something quietly astonishing in the fact that the shadow we photographed in 2022 is a portrait of an object as it existed when human beings were still making stone tools tens of thousands of years before the first city, before the first written word. One more piece of the naming story before we move forward. Sagittarius A was first identified as a distinct compact radio source in February 1974 by two astronomers at the National Radio Astronomy Observatory, Bruce Balick and Robert Brown. The broader Sagittarius A radio complex, a busy region at the Galactic center, had been known for years. But what Balick and Brown resolved was a point-like source within it, brighter and more compact than the surrounding emission, sitting right at the dynamical center. They called it Sagittarius AI, the asterisk added by Brown specifically because the source seemed, and here we can appreciate a scientist's understated enthusiasm, exciting. The asterisk was a mark used in atomic spectroscopy to denote an excited state. Brown borrowed it. The most massive object in our galactic neighborhood got its distinctive punctuation mark because it seemed, in 1974, to merit a small flourish of excitement. 50 years later, that asterisk has been weighed, imaged, linked to a Nobel Prize, and revealed to have been, within the past few million years, anything but the dim and retiring presence it appears today. And so we arrive, at last, at what Sagittarius A is doing right now. The answer, given everything we have traced together tonight, the hourglass scar above and below the galactic disk, the still glowing ribbon of the Magellanic Stream, the decades of patient stargazing, the planet-wide telescope that caught a shadow the size of a donut on the moon? The answer is, in a word, almost nothing. Almost nothing, and yet not quite nothing. That distinction matters enormously, and we will get there slowly. Sagittarius A today is, by every technical measure, radiatively quiescent. That is the polite astronomical way of saying it has gone almost completely quiet. The luminosity we measure from the galactic center, the light and radio waves and X-rays actually pouring out of the region immediately around the black hole, is extraordinary in its smallness. It sits at roughly 1/billionth of the Eddington luminosity. Let us stay with that number a moment because it deserves to be felt rather than merely stated. The Eddington luminosity is a theoretical ceiling. It is the brightness at which a black hole's outward radiation pressure would exactly balance the inward pull of gravity on the gas falling toward it. The point where the engine is running at its theoretical maximum, where every gram of infalling matter is contributing as much radiated energy as physics will allow. For a black hole of Sagittarius A's mass, 4 million times the mass of our Sun, that maximum output is immense, truly staggering. The kind of brightness that would make the galactic center a beacon visible across hundreds of millions of light-years of space. Sagittarius A is radiating at 1/billionth of that. If you imagine the Eddington luminosity as the full, roaring output of a vast industrial furnace running at capacity, then what Sagittarius A produces today is roughly the warmth of a single candle left sitting in a very large, very cold warehouse. The furnace is there, the fuel lines exist. The structure that could in principle generate continent-igniting heat is all present and correct. But the flame, right now, is barely a flicker. Part of the reason for this is how the whole is being fed. Or rather, how little it is being fed and how inefficiently. The material that does fall towards Sagittarius A does not arrive in a clean, orderly stream. The galactic center is a turbulent, crowded environment. Massive young stars, stellar winds, wisps of ionized gas, molecular clouds threading through the central parsecs. But despite all that activity, the amount of matter that actually makes it all the way down to the black hole's event horizon is extraordinarily small. Estimates put the accretion rate at somewhere between 10 to the power of -9 and 10 to the power of -8 solar masses per year. To translate that into something more tangible, the mass equivalent of roughly one small asteroid or large comet consumed per day. The Sun, by contrast, fuses hundreds of millions of tons of hydrogen into helium every single second. Sagittarius A, the 4 million solar mass titan at the center of the Milky Way, is subsisting on what amounts to cosmic table scraps. And even that trickle is not converted to radiation efficiently. The accretion process around Sgr A is what physicists call a radiatively inefficient accretion flow, sometimes abbreviated RIAF. In a standard, well-fed accretion disk, infalling gas grows dense and hot and radiates copiously, converting a significant fraction of its mass energy into light and X-rays. That is what you see around well-fed quasars and active galactic nuclei, blazing disks bright enough to outshine entire galaxies. Sagittarius A operates in a different regime entirely. Its accreting gas is so thin and hot and low density that it cannot cool efficiently. Rather than radiating its energy away, the hot plasma tends to hold on to it, and a large fraction of the infalling material is actually ejected, blown back outward in outflows before it ever crosses the event horizon. The whole is, in a very real sense, a fussy, reluctant diner. Most of what approaches it is turned away at the door. This is not a failure, this is, in its way, a precise and elegant physical situation. radiatively inefficient accretion flows have been studied carefully by theorists, and the observations of Sgr A match the predictions beautifully. The equations describe a black hole that should be almost invisible given what it is being asked to consume, and almost invisible is exactly what we find. Almost. Because there is a flicker, a low, persistent, sometimes surging pilot light that observers have been watching for decades now. Even in its quietest state, Sagittarius A produces flares. These are not the colossal eruptions we have been tracing from the fossil record, not the Seyfert-level detonation that lit the Magellanic stream or inflated the Fermi and eROSITA bubbles. These are small events, brief and local, lasting anywhere from a few minutes to a few hours, but they are real, and they are measurable, and they happen, essentially, every day. The gravity instrument, the extraordinary optical interferometer installed at the Very Large Telescope Array in Chile, the same instrument that tracked the S-star orbits with such exquisite precision, has watched Sgr A brighten in the near-infrared on timescales as short as 30 minutes. The Chandra X-ray Observatory has caught it flaring in X-rays, occasionally brightening by factors of 10, 20, 100 within single observation windows. In 2024 and 2025, observations with the James Webb Space Telescope revealed something remarkable in its own quiet way. Sgr A flares essentially constantly, cycling through varying intensities of near-infrared emission in a way that never really switches off. It is not silent between the big flares, it is always doing something. A low murmur of activity that occasionally breaks into a brief shout. The physics of these daily flares is still being worked out, but the leading candidate involves the behavior of gas and plasma very close to the event horizon. Magnetic field lines in the infalling material can become tangled and then suddenly snap into a new configuration to do a process called magnetic reconnection, and releasing energy rapidly as a burst of radiation. Think of it a little like the way a stretched rubber band snaps when it breaks. Potential energy stored in the tension releases all at once. Near the event horizon of a black hole, that snap is an X-ray flare gone within the hour, leaving the system looking nearly as quiet as before. These daily flickers are, in one sense, reassuring. They confirm that the hole is there, that accretion is happening at some low level, that the physics we expect to see in the immediate vicinity is operating as predicted. They are a heartbeat, irregular but present. But they also raise a question that leads us directly to the most important lesson the Galactic Center has to teach. A heartbeat can accelerate. You may have heard at some point the story of G2. In 2011, astronomers studying the central parsecs of the galaxy noticed something. A diffuse, elongated blob of gas and dust, a cloud essentially, though possibly with a faint star at its heart, moving on a trajectory that would bring it very close to Sagittarius A. Disturbingly close. The object, catalogued as G2, was calculated to make its closest approach in 2014, sweeping to within a few hundred astronomical units of the black hole. The anticipation built over the following years. Press releases used words like fireworks. Astronomers booked telescope time on multiple instruments across multiple observatories. There was a genuine, excited expectation that Sagittarius A was about to be handed a meal, that G2's encounter would drive gas into the accretion zone, spike the feeding rate, and produce something spectacular. Maybe the daily flares would intensify dramatically. Maybe there would be a brief but vivid brightening, a small echo of the kind of activity that inflated the Fermi bubbles, something visible in real time across the electromagnetic spectrum. 2014 arrived, G2 made its closest approach. Sagittarius A barely reacted. G2 stretched and deformed under the tidal forces near the hole, as expected. Its elongated shape grew more pronounced as the gravity gradient pulled at its near and far sides, but the material did not plunge in. The flares did not intensify dramatically. The black hole did not eat. The anticipated fireworks were, in astronomical terms, a damp squib. G2 survived the encounter largely intact and continued on its way. The lesson was quietly humbling. Sagittarius A is not simply waiting for something to approach. The dynamics of feeding a black hole are complicated, and the geometry of angular momentum is almost perversely uncooperative. To actually fall into a black hole, material does not just need to come close. It needs to lose most of its angular momentum, the rotational inertia that keeps it orbiting rather than spiraling in. Sending gas on a trajectory that passes near the hole is easy. Getting that gas to actually cross the event horizon is far more difficult. G2 approached, but it retained enough orbital energy and angular momentum to swing around rather than fall through. This is, in a way, a useful corrective to a very common misconception about black holes. There is a persistent image, intuitive, understandable, but wrong, of a black hole as a kind of cosmic vacuum cleaner. A drain in space, relentlessly sucking in everything around it, an insatiable mouth that consumes whatever comes near. It is a compelling mental model. It is also not how gravity works. Gravity, including the gravity of a 4 million solar mass black hole, operates by the same inverse square law as every other gravitational field. Matter in orbit around Sagittarius A, the S-star cluster, the molecular clouds threading the central parsecs, the stellar winds gusting through the region is orbiting, just as the Earth orbits the Sun without falling into it, just as S2 swings around its 16-year ellipse and comes back again intact. The hole does not reach out and grab. It sits at the center of a gravitational well, and things orbit it, and some fraction of that material gradually loses energy through interactions and slowly spirals inward over vast timescales, and an even smaller fraction of that fraction makes it all the way to the horizon. If tomorrow morning the Sun were magically replaced by a black hole of exactly the same mass as the Sun, which is not 4 million solar masses, not a supermassive giant, just a solar mass black hole, the Earth would not be sucked in. It would keep orbiting exactly as it does now, in the same path, at the same speed, utterly unperturbed, except for the absence of sunlight and warmth. The hole would not vacuum the Earth up. The Earth would orbit it in the dark until something else perturbed the orbit. Sagittarius A is vastly more massive than that. But at the distance of 26,000 light-years, its gravitational influence on our solar system is negligible. We are not circling a drain. And even if Sagittarius A were to wake up again, if something were to reignite it, push it back toward the luminosity it briefly reached 3.5 million years ago, the effects at our distance would not be catastrophic. Not even close. At 26,000 light-years, even a Seyfert-level flare, an active galactic nucleus burning at tens of thousands to millions of times its current output, would arrive at Earth as a very faint signal, possibly faint ionizing radiation, possibly a barely perceptible enhancement of the high-energy photon background, certainly not a sterilizing event, not a threat to the biosphere. The speculation about a faint sky glow over our ancestors during the last major outburst, the idea that the night sky over Australopithecus might have carried a ghostly brightness near the galactic center, is a reasonable inference from the physics, a thought worth sitting with, but it represents something subtle and atmospheric, not something that would have been felt on the ground. At 26,000 light-years, even a roaring galactic nucleus is very, very far away. So let us set the fear aside, because the genuine story is far more interesting than the fearful version. The question, could it wake up again, is real. The answer is yes, it could. And the mechanisms by which that might happen are worth understanding because they reveal something beautiful about how the quiet galactic center is actually organized. The most straightforward trigger for a new outburst would be a sudden increase in the amount of material reaching the black hole's immediate environment, a spike in the feeding rate large enough to push the accretion process out of its current radiatively inefficient regime and into something more productive. There are several ways this could happen. The first involves gas clouds. The central parsecs of the galaxy contain molecular gas, dense, cold, massive clouds threading through the region. Under the right circumstances, a cloud or part of a cloud could lose angular momentum through interactions with other material. Collisions, gravitational perturbations, encounters with the stellar winds from the dense young star clusters near the core, and begin a genuine inward spiral. If a substantial mass of gas found its way into a tight orbit and then began to accrete efficiently, the feeding rate could spike by orders of magnitude. G2 did not cooperate in 2014, but the galactic center is not short of gas clouds and the dynamics play out over millions of years. G2 was one near miss. The process continues. The second mechanism is more dramatic. If a star wanders too close to the event horizon, close enough that the tidal gradient, the difference in gravitational pull between the near and far side of the star exceeds the star's own self-gravity. The hole tears it apart. Literally. The outer layers are stripped away, drawn into a swirling disk of debris, and the resulting glut of material falls inward in a bright, furious accretion event. This is called a tidal disruption event, or TDE. Tidal disruption events have been observed in other galaxies. Brief, bright flares of X-ray and ultraviolet radiation from galactic nuclei that were previously quiet, signatures of a star that came too close and paid the ultimate price. Sagittarius A is surrounded by a population of stars, the S-star cluster, and beyond it, the broader nuclear stellar cluster. Any of those stars, if perturbed into an orbit that brings it too close, becomes a potential fuel source. The third possibility involves the material that is already orbiting close in. Surrounding the black hole, there is a structure called the circumnuclear disk, a ring of dense molecular and ionized gas at a radius of a few parsecs rotating around the center. This disk is not currently raining material onto the hole at high rates, but it is there, orbiting, subject to instabilities and perturbations. A gravitational disturbance, a close stellar encounter, a particularly energetic outburst from one of the massive young stars embedded in the region could in principle destabilize part of the circumnuclear disk, driving material inward on a timescale short enough to noticeably spike the accretion rate. And the fourth is perhaps the most chaotic: stellar collisions near the core. The nuclear star cluster at the galactic center is one of the densest stellar environments in the Milky Way. Stars are not perfectly isolated there. They move on complex intersecting orbits at high velocities. Collisions and near collisions between stars can produce streams of disrupted gas. That gas, depending on how it is ejected, can, in some fraction of cases, find its way inward toward the hole. None of these triggers is inevitable in the short term. None of them is imminent, as far as we can determine. The galactic center is not on the verge of reignition in any human sense of soon, but on galactic timescale, over the next millions to tens of millions of years, one or more of these mechanisms will almost certainly provide enough material to temporarily reignite Sagittarius A. The question is not whether it will happen. The question is only when and which trigger will be the one that finally breaks the quiet. The X-ray light echo that was detected bouncing off the Sgr B2 molecular cloud, that evidence suggesting Sgr A was 10,000 to 1,000,000 times brighter only a few hundred years ago, a much smaller and more recent outburst than the one that inflated the bubbles, suggests that the hole may have had minor episodes of enhanced activity even within recorded human history. not civilization-threatening, not even particularly dramatic by galactic standards, but real. The echo of a modest flare, its light still traveling outward, bouncing off gas clouds and eventually reaching our instruments. That is a remarkable thing to hold in mind, a flashback from a few centuries ago, written in reflected X-rays, arriving at our telescopes in the 21st century. And so we find ourselves looking at a system that is, by any measure, layered in time. The light we used to make the 2022 Event Horizon Telescope image left the galactic center 26,000 years ago. The X-ray echo suggesting a minor outburst a few centuries back is reaching us now, after bouncing off a molecular cloud. The Magellanic stream is still glowing from a flare that happened 3.5 million years ago. The Fermi bubbles and the eROSITA bubbles are still drifting outward, colossal, slow structures expanding at a few hundred kilometers per second into the halo of the Milky Way, carrying the energy signature of an event that may have occurred between 2 and 6 million years in the past. The galactic center is not a place we can visit. It is a place we read, like archaeologists reading a site where the artifacts are made of light and gas, and the timescales are measured in millions of years. Every observation is a letter that has been traveling toward us for a very long time. Every measurement is a piece of a story that was already ancient when the first hominin stood upright on the East African savanna. There is a particular quality to this kind of knowledge, the kind that comes from reading echoes and shadows rather than watching events in real time. It is slower than most science. It requires patience on a scale that can be difficult to fully imagine. The teams that tracked the S-star orbit spent 30 years watching stars move, accumulating data, one observation at a time, building up the picture of a 4 million solar mass object from the graceful curves of a few dozen stellar paths. The Fermi Gamma Ray Space Telescope spent years surveying the sky before Doug Finkbeiner and his colleagues had enough data to recognize that those two enormous lobes of gamma-ray emission were really there, really symmetric, really centered on the galactic core. The eROSITA instrument on the Spektr-RG spacecraft had to map the entire X-ray sky before the larger shells became legible. Joss Bland-Hawthorn spent years working through the calculations, connecting the glow of the Magellanic stream to a Seyfert-level flare of Sgr A, revising the models, tightening the numbers, publishing in 2013, and returning with refined estimates in 2019. The Nobel Committee did not award Reinhard Genzel and Andrea Ghez until 2020, decades after they began their respective observing campaigns. None of this was quick, none of it was simple. And yet here we are, tonight, with all of it in our hands. We have weighed a black hole we cannot see by watching a star orbit it so fast it grazes 2.5% of the speed of light. We have photographed the shadow of its event horizon across a distance of 26,000 light-years using a telescope assembled from radio dishes on 6 continents, synchronized by atomic clocks, its data shipped across the planet on hard drives because no network connection was fast enough to carry it. We have found the fossil record of a past awakening, not in rock, not in sediment, but in the glow of gas tens of thousands of light-years away, still warm from a fire that burned before our genus existed. And we have identified, with reasonable confidence, the mechanisms that could one day restart that fire. Let that settle for a moment. You are lying somewhere comfortable right now. Your room, your bed, whatever dark and quiet place has carried you this far into the night. And somewhere overhead, buried inside the faint smear of the Milky Way, lost in the ordinary glow of 1 billion stars, there is a point in space where 4 million solar masses have collapsed into something smaller than our solar system. Right now, at this moment, it is eating approximately 1 asteroid's worth of matter per day. Every few hours it flickers, producing a small burst of X-rays or near-infrared light that our telescopes can catch if they happen to be pointing in the right direction. And 25,000 light-years above the galactic disk, two enormous lobes of gamma-ray-emitting gas are still slowly drifting outward, the long exhale of an explosion that happened before your earliest traceable ancestors, before the genus Homo, before stone tools, in a world where the footprints being left in East African mud belonged to Australopithecus. That glow is still moving. It will keep moving. The bubbles will not stop. And the black hole, for now, sleeps. Or rather, it murmurs. It does not sleep in any complete sense. It flickers and stirs. The circumnuclear disk revolves around it, patient and dense. The S-stars continue their orbits, tracing their invisible ellipses at speeds that would carry you from Earth to the Moon in 50 seconds. The infalling gas that manages to approach the event horizon mostly gets blown back out, rejected, ejected in outflows before it can contribute to the accretion. And somewhere in the galactic center, right now, gas clouds are moving on trajectories that might, in 1 million years or 5 million years or 50 million years, bring enough material inward to change everything. We will not be here to see it in any direct sense. The distances and the timescales make that impossible, but the evidence we have gathered, the fossil record written in bubbles and glowing gas and bounced X-rays and the slow dance of stars, tells us that this galaxy has a heartbeat, and that heartbeat is not always quiet. It has roared before. It will, in all likelihood, roar again. And here is the thing that I find most worth carrying into sleep on a night like this. The atoms in your body, the carbon in your cells, the oxygen in your lungs right now, the iron moving through your bloodstream, were not manufactured here. They were forged in stars that lived and died long before the sun existed. Some of those stars lived and died near the galactic center. Some of the stellar debris that eventually found its way into the molecular cloud that collapsed to form the sun and the planets may have passed, at some point in its long journey, through regions lit by the galactic center's activity. The iron in your blood is old. The carbon in your DNA is old. The galactic center's history and your body's history are not separate stories. They are the same story, written in different chapters and in very different handwriting, but continuous. The Fermi bubbles are still expanding into the halo of the Milky Way. The Magellanic Stream still carries the ionization signature of a fire that burned 3.5 million years ago. The Event Horizon Telescope captured a shadow that the light left during the last ice age. And here you are, a temporary arrangement of ancient stardust lying still in the dark, listening to the long story of the thing at the center of the wheel you are part of. You are not outside this, you are inside it, you always have been. There is something the darkness does in moments like this that daylight cannot quite manage. It makes the distances feel real rather than abstract. 26,000 light-years is a number that slides past without traction when you read it in the afternoon. But in a quiet room, late at night, with no particular urgency, it can become something felt, a genuine sense of depth, how large the space is that you are floating in, and how strange and specific the patch of it you occupy happens to be. Roughly 26,000 light-years from a sleeping giant, on a small rocky planet circling an ordinary star, in the outer reaches of one of the galaxy's spiral arms, safe for now and for the foreseeable future from the violence that the galactic center is capable of, that it has already demonstrated it is capable of in the record written across half the sky, and yet connected, deeply, indelibly connected. The astronomer who first pinpointed Sagittarius A as something worth the asterisk, Robert Brown, in 1974, could not have known sitting at the National Radio Astronomy Observatory, what the next 50 years of science would read in that compact radio source. He noticed that it was exciting. He borrowed a mark from atomic spectroscopy because the source seemed to deserve a small flourish. And the small flourish turned out to be one of the most consequential pieces of punctuation in the history of astronomy. The teams that watched the S-stars move, Genzel and his colleagues at the Very Large Telescope, Gez and her colleagues at the Keck Observatory, spent decades doing something that, on its face, sounds almost impossibly patient. Watching stars move, waiting for orbits to close, building up a picture, one observation at a time. They did it because they believed that what was at the center of those orbits was worth understanding. And they were right. The Nobel Committee agreed. In 2020, the rest of us get to inherit the picture they built. The people who built the Event Horizon Telescope, who synchronized radio dishes across 6 continents, who shipped petabytes of data on hard drives by cargo plane because the internet was not fast enough, who coaxed an Earth-sized virtual lens into focus with atomic clocks and very long baselines and an extraordinary amount of careful, collaborative, patient work. They gave us something that no human being had ever seen before, not even in principle, not even as an artist's impression. An actual image of the actual shadow of the actual event horizon of the black hole at the center of our galaxy, the place where, if you could fall toward it, the escape velocity would exceed the speed of light, and space-time itself would close around you. We have seen it. Not perfectly, not in high resolution, not in a way that reveals every detail of what happens just inside the shadow's edge. But we have seen the shape of the darkness. We have confirmed, as well as current instruments allow, that what sits at the center of the Milky Way is exactly what general relativity predicts it should be. The equations written down by physicists in the early 20th century, long before anyone imagined we would ever be able to test them at this scale, described something that actually exists, and that we can now point to with a specific image and a specific date, May 12th, 2022. All of that is real, all of it happened. And back at the start of this long night together, I asked you where you were listening from. I still wonder. It is genuinely one of my favorite things about nights like this. The thought that somewhere in the world, wherever this finds you, someone is lying in the dark and thinking about the thing at the center of the galaxy. In a city that is still lit at the edges, or somewhere much quieter, where the Milky Way might actually be faintly visible if you went outside and let your eyes adjust. Under a different season than I imagine, a different time zone, a different kind of quiet. The Fermi bubbles are there right now, above and below your sky, whether you can see them or not. 25,000 light-years above the galactic plane and another 25,000 below, the long, slow exhale of a fire that burned before your family tree had a trunk. They are not going anywhere in any time frame that would matter to any living thing on this planet. They are just there, drifting, fading very slowly as the energy disperses into the intergalactic medium, and the hole at the center is murmuring, an asteroid's worth of matter today. A small flare sometime in the next few hours, probably, if past patterns hold. The S-stars wheeling on their invisible rails, S2 somewhere on its 16-year ellipse, closer or farther from the center depending on where in its orbit it happens to be right now. If a gas cloud finds its way inward, if a star wanders too close, if the circumnuclear disk develops an instability that sends material spiraling in, the murmur will become something else. The accretion rate will spike. The radiatively inefficient trickle will be flooded with new material, more than the inefficient flow can simply eject. And Sagittarius A will, for a time, perhaps thousands of years, perhaps hundreds of thousands, perhaps less, become an active, galactic nucleus again, a Seyfert galaxy. The galactic center will blaze. The bubbles that are still expanding from the last time will be joined, eventually, by new ones. At 26,000 light-years, we will be fine. The light will arrive, faint, diffuse, scattered by the gas and dust between us and the center. Not a catastrophe, not a crisis. Just a brightening, probably below the threshold of naked-eye visibility, a slight enhancement in the X-ray background, perhaps detectable by the descendants of the instruments we have now. But the sleep of the giant is finite. That is the truth the fossil record has handed us. Not the sleep of the dead, but the sleep of something that has roared before, that carries within its structure the capacity to roar again, that is only quiet right now because the feeding has, for the moment, slowed to a murmur. That is enough to know. That is honestly a remarkable amount to know. And so if you are still with me, if the night has carried you this far through the galactic center, through the Fermi bubbles and the Magellanic stream and the S-stars and the shadows and the naming stories and the patient watching and all the slow fossils of ancient light, then I hope you are carrying something with you into sleep that you did not have when you closed your eyes. Not fear. There is no fear warranted here, not urgency. There is nothing you need to do about any of this, just a quiet sense of the scale of things, the depth of time, the patience that the universe brings to all its largest projects. You are made of the same physics as the gas that is slowly feeding the black hole at the center of the galaxy. The same quantum fields, the same atoms, the same fundamental interactions that keep a photon moving at the speed of light, and keep a star burning, and keep S2 swinging through its 16-year orbit, are the ones holding you together right now. The galactic center is not separate from you. It is the same story you are part of, written in a larger hand on a longer timescale, in a register that is harder to hear but no less real. The Fermi bubbles are still expanding. The Magellanic stream is still glowing. The event horizon. Telescope's image is still traveling through the archives and the textbooks and the minds of the next generation of astronomers who will go further than we have. And you are here, right now, in the dark, at the end of a long, slow journey through all of it. That is a good place to be. If this slow journey through the galactic center gave you something tonight, a little wonder, a little peace, a sense of the large and quiet things, a gentle like or subscribe helps this channel keep going. Small creators like me really rely on your support to keep these nights coming. And I would love to know where you are listening from and what time it is in your corner of the world. Leave that in the comments if you feel like it before you sleep. Until next time, stay as long as you like in Nightoria. Good night.